Get started. So welcome everyone to this is our first workshop that's been run under the banner of ACQI, and just welcome to everyone who's joining us on Zoom. Thanks for making the time. I guess why we created this workshop was because a lot of groups are starting to collect imaging data as part of trials, or maybe are thinking about doing so, and maybe thinking about the types of analysis that can be done on this data to help translate their outcomes, maybe derived from biomarkers that might be clinically useful. So what we wanted to do was create some knowledge around some of the issues associated with collecting these data, how we make sure it's good quality, how we make sure it's going to be useful, and then what we can actually do with it once we have it. So I'm going to kick off with the very tedious and boring part of governance around collecting these data in the first place, and the sorts of logistics that you need to be able to do that in an efficient way. And Nathaniel's going to talk about how you prepare that imaging data for analysis, and particularly the field of radiomics, which some of you may or may not be familiar with, which is extracting features from the images that might be useful for diagnostics or prognostics. Jake's going to talk about then using those features in machine learning models to produce diagnostics or prognostic models. And then Brian's going to look at the very exciting new world of deep learning, and then how that can be applied on clinical data, on imaging data, to derive predictive models. I have to recognise that this is a very diverse audience. There'll be those amongst you to whom this is completely new. There'll be those amongst us who are more expert than I in this field. So we've tried to pitch this, I guess, at that lowest common denominator. So we're assuming that there's not too much knowledge attached, that you don't have too much knowledge about how to do image processing or analytics. So we won't talk heavily about coding, about things called Python and other nasties, which the experts can use to implement an analysis on your data. So I just come with this warning on the right here that the material will rapidly get heavier, but it is pitched to be understood by the non-experts. Okay, so I'll start off by talking about how we collect the data, and so why we might collect the data. And I guess there's two possibilities. One, it might be the primary objective of your study, and the other one, it might be a secondary analysis concept. So we might be using imaging as a way of looking at outcomes in our population. We might be using it to stratify our patients, or the actual trial itself may be focused on some aspect of imaging analytics, such as a deep learning tool, for example, to assess progression, and then that becomes the thing we're actually testing in the trial. But the secondary analyses may be enabled by the trial. So we may collect imaging data, we may be looking at some primary objective, some primary outcome, and the fact that we've coincidentally collected imaging gives us a pathway to translation, and we can use that imaging to develop biomarkers and develop means of translating that outcome into practice. Another reason to employ imaging analytics is because it's a very rich source of data that we can use to describe disease. So again, Nathaniel will talk about radiomics and what it is, but basically radiomics is a subset of phenomics, so the physical expression of the underlying genome. And radiomics can be used as a surrogate, therefore, for the molecular nature of the disease that we're looking at. We'll just try to show on this diagram how it relates to biopsy. So if we consider how often we can use a technique, what sort of spatial information it gives us, and how specific the information is that it gives us. Solid biopsy might be very specific, but spatially it's very localized to one point. And temporally it might be localized as well. We can't necessarily do solid biopsies frequently. Liquid biopsies we can take perhaps more frequently, but has fairly poor spatial resolution, that we don't know where in the body that systemic marker may have originated. So molecular imaging helps us span that space somewhat, But imaging could have variable specificity, but we can generally image with reasonable frequency, and it gives us spatial information from the millimetre scale up to the whole extent of the body. So this would span a fairly large proportion of this space. It's very rich data, so we can look at everything from an individual image voxel all the way through to an entire trial cohort, and maybe even between trials. So it gives us a large space to search from, to look for markers of progression or diagnosis. In fact, there's more combinations of information in a patient's imaging series than there have ever been human beings on the planet. That's how many permutations there are in that data. So we're never going to be able to power a trial to look through all of that, but it's certainly a very rich source of data. And then you can add the fact that we can image with more than one modality. We can image with CT and MR, multiple sequences of MR, with PET, different PET traces, dynamic PET, and then we can also look at the underlying data that forms those images, the raw data. And so this can all be mined for sources of potential biomarkers. Then the applications. So I think most of you were probably here for this morning's symposium, where we looked at a large variety of applications spanning pathology work through preclinical imaging, right through to patient information. So we can use these techniques in a wide variety of settings across multiple medical specialties for multiple purposes. Another reason to employ it is because this is a rapidly growing area. So there's about a 6% per annum growth in just the imaging field. But if we add the analytics side onto that, we're looking at new pathways, new treatment pathways emerge, and more demand for imaging in different ways. And that's, of course, going to drive that growth even further. So this first talks about how we collect the data. So basically what we want to make sure is that we get quality image data that's collected in a controlled, safe way, that's approved under governance principles, that we collect the relevant covariates that we need, and probably the thing that I find most important is that we make it fair, make it findable, accessible, interoperable, and reusable, so that we can get the best value out of this data, which has taken a lot of effort to collect in the first place. So we're just going to run through some of the steps in that process. So I guess the first one is making sure we can actually access imaging resources to collect the data in the first place, because retrospective collection of imaging data can be really, really hard. Hard from a governance perspective, hard from the logistic of actually obtaining the images, and then very hard from a quality perspective. So you can consider the cost required for that access, which might range from about $400 per CT scan to $1,200 plus for a PET image. And so this has to be factored in to the design of any study, unless you're fortunate enough to get these resources for free. And just note that some imaging may be covered under the NBS if the patient's treatments are not being modified for what would be the clinical standard. You can consider access to clinical scanners. So if we can access scanners in situ in public hospital facilities, for example, that's fine. In future, we'll be able to have access here to research scanners, MR and PET scanners on the third floor, as Paul Paratel described this morning. So we'll have actual access to dedicated scanners. But private radiology can also provide access to scanners for research purposes. We have to be able to export the imaging data from wherever it's collected, and we have to be able to look at how imaging on one scanner relates to imaging on every other scanner, and we call this the harmonization process, which is vital for translating it. So basically, we want to make sure that the imaging we perform on our single institutional scanner, if a patient's imaged there, we're going to get the same image as if they were imaged on scanners somewhere else. And so this is very important if we want to derive a quantitative biomarker that's going to be equivalent no matter where a patient is scanned. And then, of course, we want that to be equivalent to the same scan performed anywhere in the world, so that biomarker can be translated anywhere. And there's a couple of different ways to do this. One is to take the same person and have them imaged on every scanner with the same technique and see that we get the same result. That's problematic because it's very expensive and there aren't volunteers necessarily to do that. They may involve multiple contrast injections, they may involve exposure to radiation, they may involve exposure to tracers. So it's essentially impractical to do that. So generally we'll do what's called a phantom study. So there are generic designs for plastic, water-filled, other agent-filled phantoms that can be scanned on multiple scanners, and in concept we should get the same result if those scanners are harmonized. So we certainly can't send that human around the world to harmonize imaging, but we can manufacture phantoms the same anywhere in the world and ensure that we get the same scanners. And there are organizations like NEMA, the National Electrochemical Manufacturers Association or something like that, that define how these phantoms can be created in standardized ways. We have to think about where in the patient's journey the imaging is going to happen and standardize that as much as possible. So this is an example of a timeline from a study Ros talked about this morning called the FIG study, PET in glioma, where patients have surgery and chemo, and they actually have some imaging before that. This is the post-treatment imaging schedule. And you can see there's very specific time points at which patients have imaging of very specific types, and we describe quite clearly where those images are going to go. So as with any trial, protocol development is important, and it's important to standardize it. The Equator resource is a fantastic site to get standards documents associated with trials. So there's the Spirit document example of saying what standard items should be in a protocol, and just note there's a new AI extension to that now. So if your protocol involves AI in some way, there are new ways to define those protocol items. We would suggest having a dedicated imaging manual that makes it very clear what the imaging process involves, including context for technical questions, what pre-trial quality assurance is being performed on the imaging systems, what certification centres might require to participate. So there are various organisations that can certify scanners that they're calibrated and quality controlled to participate. Be very clear about the imaging schedule, details of any. If you close the door. Details of any ancillary requirements, particularly with PET tracer manufacturer, that's been standardised and the manufacturer has been certified for that tracer. Anything specific to the imaging session, so that whether the patient has to, for example, have a full bladder or not. And this is an unfinished sentence, which is meant to say something along the lines of any required imaging sequences or positions of the patient that need to be considered in each imaging schedule, any markup instructions, so how these images need to be labelled locally before they're sent for analysis, any local reporting that needs to be done. So RECIST, for example, is a way of assessing tumour response, so whether that needs to be done locally before the images are sent. And any imaging processing and handling that needs to be performed. And a typical image processing stage would be a de-identification of the images before they're submitted. Consider case report forms. There'll typically be a CRF collected at each imaging session. Note that images in contemporary formats, the format we use these days is called DICOM, comes with a header. Those images have information about the patient, about their treatment, about the centre they were at, about the scanner, the characteristics of the image. That's all contained in this image header. Some of that will be stripped away at de-identification. And so sometimes we collect information on the patient, such as weight, for example, that can be stripped from their head while it's being identified. We might have information in that CRF about when the scanner was calibrated last and what the result of that was, any departures from the imaging protocol, and then the results of any analysis. And then there's the quality control of the images and how they're read. Just an example, we might have what's called real-time review or near real-time review, whereby an image is acquired, and if that image needs to have a decision made on it before the patient can progress in the trial, that might need to be reviewed by the trial investigators. So in this FIG study, for example, we have imaging at this time point at suspected progression of disease. Those images are acquired and interpreted by the local clinicians. Then they're uploaded and assessed by the trial investigators independently, who in concept are more expert at making that call than the local clinician who may not have experience in it. And then they can feed back that information before the patient progresses to the next stage of the trial. Patient information and consent is important for the reasons it always is in clinical trials, just acknowledging the fact that we're collecting large amounts of data which are really, really useful for lots of purposes. So I'd suggest making sure that the patient information and consent form indicates the data may be used by collaborators and students, may be used on commercial or research cloud systems. So in Australia, we have, for example, cloud store system, but it might also end up on private or industry founded commercial cloud systems such as AWS and Azure. The individual images themselves may be used in presentations and publications or for education purposes. That the images may be used for commercial purposes, so developing products. That typically will remove personal health information from images before it's moved anywhere. There are some exceptions where patient level identifying information needs to be stored, and we'll talk about that in a second. We need to think about how incidental findings might be handled. So if we're acquiring images that aren't normally acquired as part of the patient treatment process, we may make findings that we weren't expecting. So how do we handle those? How much time the patient's going to have to commit to performing studies. If they're doing a couple of different PET studies, they may be at nuclear medicine for a large part of the day, for example, that they otherwise wouldn't need to be in hospital, and what interventions they might be subjected to. In terms of ethics and governance, imaging dose can be very important. So some of these imaging acquisitions, not so much CT anymore. CT used to be a large contributor of dose. These days it's kept fairly low, but certainly PET imaging and SPECT can add reasonable amounts of radiation dose that patients otherwise wouldn't receive. For most ethics committees, it's certainly for the local ethics committees here, you need certification from a licensed physicist to make an assessment of what dose these patients will receive. Consider the contrast and tracer tolerance. So gadolinium contrast, for example, multiple gadolinium contrasts have been associated with various adverse effects. The cost, if there are non-MBS scans involved, where that cost is going to come from, and the participation inconvenience. As I've said, some of these image acquisitions can take large parts of a day. Again, for me, this is an important part of ethics, is that the data will be fair, it'll be made accessible, that it'll be in formats that are interoperable and reusable, and that the data is going to be findable, so that other groups developing their own technologies who may want to validate on your data set can access it. They know it's going to be in a certain form, they know it's going to be accessible, and they know they're going to be able to run their algorithms on it accordingly. For ethics and governance, where the data goes, as I mentioned, is quite important. Just run through a couple of case scenarios. For example, we might be collecting data within WA Health. So WA Health has a nice cloud computing environment. It's actually called Health Next, run by a company called ATOS. So we can collect information within that environment quite easily. We can actually collect identifiable information within that environment and can analyse it internally. And we could even bring data from external sites if those sites have ethics approval to do that. So this is probably the safest, simplest and most secure way we can collect data. This may be just on the hospital PACS system. If we want to move it outside of that environment, it becomes obviously more problematic. So if we're moving outside of health, we're collecting data from external sites as well. If we're taking that onto what we call non-HIPAA approved or non-ISO 27000 approved storage facilities, then we need to make sure that that data isn't identifiable in any form. But that is actually a much more convenient way to access data and process it and make it available than keeping it within inside a hospital firewall. Another option is to actually put it onto an approved environment, such as AWS, but there's a significant cost attached to that for moving that data there and then actually processing it on AWS computing resources. Probably the lowest level of security and the poorest governance is if you want to move this data to a publicly accessible repository. In that case, most definitely we need to remove all the identifying information and have consent approval to do that. So this is one public website, for example, called the Cancer Imaging Archive, maintained in the US, funded through NIH, where you have publicly accessible data sets, but I'm yet to be involved in a study that's had permission to move data onto that sort of resource. And the last case scenario is where we make only the metadata findable. So this is where we take only the information describing the participant cohort and what's they've been involved in, and make that information findable on a published site. So, for example, in Australia, the ARDC is going through a program of establishing ISANDA, which should be an environment in which this data should be discoverable for those looking for it. And I just note that sometimes publication of that metadata may be a requirement from your funder or for a journal publication. So data identification can be a multi-headed beast. At the very base level, as I said, DICOM formatted data, which is what most imaging comes with now, has a header, and that header has information about those individual patients, which can be quite specific, down to their name, date of birth, etc. So, and that is quite easily readable in its raw form. It's not encrypted at all. So that has to be considered. So generally what we'll do is de-identify that information. So replace all of the potentially identifiable information with just null strings, or replace them with things like trial IDs, provided those trial IDs can't be traced back to the patient. And that can be undertaken often in the imaging workstation where the images are acquired, in subsequent imaging processing software, or dedicated anonymizing software, or whoever's collecting the data may have scripts in place to be able to remove that information. Sometimes the images themselves will have burnt-in information, particularly ultrasound often has burnt-in identifying information, so that has to be removed. And we're at the point now where faces can be recognised. So someone can take an MRI, reconstruct a face, do a Google search and find who that individual is. So we're doing, groups have developed things called skull stripping, for example, a very nice term. Basically, the idea being to remove those features that aren't going to be important for the subsequent analysis that the group's doing. So this is a study where this group took about 400 patient images and then found, just by reconstructing the face, and they also had photographs of those individuals, they could identify almost all of them from that process. And then they looked at different defacing algorithms to see how efficient they were at removing enough information that the patient was no longer identifiable. So it got down as low as 28%, so they could still identify individuals and what was remaining in those images. And we have to think, how long is it going to be before other aspects of anatomy are going to be enough to identify an individual? And already groups have developed deep learning algorithms that will take what's left after this process and reconstruct the face and be able to predict who that individual is. So we've got to think about those sorts of things. Statistics is often a big part of an ethics document. In imaging, there's lots of different endpoints we can use. It's rarely a case of doing a t-test and looking for a p-value change. It's often looking at ROC analysis, receiver operating characteristic analysis. There's often not hard and fast rules about what sort of patient numbers you're going to require for certain power. And the endpoint can change considerably. When we're talking about specificity and sensitivity, we might want high sensitivity and not care so much about specificity. We might want both to be high, and those things can vary a lot. So in this study, for example, they in the US, the FDA requires a high accuracy to be demonstrated. But what this group showed was that they were having occasionally decreases in accuracy, but measured by a difference in ROC curve, but an increase in the potential to diagnose the treatment. And the result, the main actual reason for those, they were detecting a lot more false positives, but they didn't care because what their algorithm was trying to do was just trying to be sensitive. So false positives were fine. So it depends on what your outcome is that you're after. Image quality is very important. So the resolution of the images, the contrast level, how those images have been processed at different points along the pathway, whether there's artifacts in there due to, for example, poor quality control on the imaging device. Bias from observers can be a big effect. If you're relying on the labels of these images from observers, you've got to account for the fact that there's bias, so we might need multiple observers to look at what the variation is. Repeatability is important. If we image the same patient twice on 2 different days, are we going to get the same image? And there are other inconsistencies, and Nathaniel will be looking at the impact of some of those. For reporting and publishing, again, I'd refer you to the Equator resource where you can get information on standardized reporting. So Consort, for example, is the typical method for reporting clinical trials. And now note there is a Consort AI extension. So for the trials reporting artificial intelligence developments, there's a standardized way of reporting those now. So just coming to the end. So just note that, as previously mentioned, we have the WA-NIF resource coming to the 3rd floor here. So we are going to have access to dedicated research imaging devices. And we formed ACQI as a way of trying to gather expertise together in the imaging analytics space to enable these trials to be supported, so that there's a pathway to making sure the trial data is consistent and collected in a reasonable way, and as a way of providing expertise to do the analysis. So ACQI's one node in a national network called the Australian Imaging Service. So the Australian Imaging Service is an installation, is multiple installations of a cloud database system for collecting imaging data in a well-governed way. So our local installation is on the Pawsey system. So basically, this is an example of our XNAP facility with, this is just sample data on there, but basically gives us a way to collect your imaging data together into repositories on a project level basis and control access to that information by those who have authorization to do so. And then we can link that imaging data to various different mechanisms for processing it. So we have tools for remotely viewing it. So trial investigators can review the images. That's linked to AI-assisted tools using a product from NVIDIA called Clara that lets you do auto-segmentation, for example. We can run image processing pipelines on those. So if you have a bespoke image processing pipeline, we can do what's called containerize it and it gets deployed onto XNet and can be run on that data. We'll have facilities for de-identifying it. We're building facilities to link it to standard image processing software, such as 3D Slicer and other software. We're yet to develop a link to REDCap. So at the moment, for the trials we're running, these are running side by side, but they're not communicating with each other. But because we're on Pawsey, we get instant access to the local Pawsey computing facilities. So thank you for your time, and just once again want to acknowledge the PICF WA Life Sciences Innovation Hub that have actually coughed up the cash to pay for the morning, afternoon tea and lunch. I really appreciate their input. So if there's any questions, I can answer them now. Or we can move straight into Nathaniel. Any questions?